this hydrogen is being substituted by the acyl group COCH3. So what happens instead of hydrogen there, you'll get the COCH3, and the hydrogen which is being replaced combines with the chlorine and forms HCl. So you have benzene here, to which we are going to add 3 moles of hydrogen in presence of finely divided catalyst like nickel. What happens? You have 3 double bonds here. Will it help in substituting the incoming group more easily? No, right? Because it is having positive charge, it is less electron rich now. Hello everyone, this is Ambli Unnikrishnan from the Department of Chemistry, Vidhyaashram Pre-University College, the Temple of Excellence, Mysore. So in the last session, we started off with the chemical properties of benzenes, right? Chemical properties of benzene. So in today's session, even we are going to continue with the rest of the chemical properties of benzene, right? As well as directing influence of functional groups in monosubstituted benzene. Also, the last topic, that is carcinogenicity and toxicity. So already we have discussed about this, right? Benzene are carcinogenic substance. So regarding that also, we are going to discuss, right? So let's continue with the rest of the chemical reactions of benzene, right? So in the last session, we studied about the Friedel-Crafts alkylation and the mechanism of that. Today, we are going to study about Friedel-Crafts acylation. The next reaction is Friedel-Crafts acylation. So, alkylation was addition of an alkyl group, right? So, what is acylation then? Addition of an acyl group. So, let's see. Benzene reacts with acid chloride in the presence of anhydrous aluminium chloride. So, in the case of alkylation also, we were using anhydrous aluminium chloride. But there we were using alkyl halide, right? For example, if I need to substitute methyl group, I take CH3Cl in that case. But here we have to add which group? We are going to substitute it with the hydrogen with an acyl group, okay? So I need to add or react benzene with something so that I'll get the acyl group from there. So what is that I'm going to use? I'm going to use an acid chloride here, okay? Why it is called an acid chloride? It is derived from carboxylic acid. Right, instead of OH, you will have the chlorine here. It's called as an acid chloride because it's a derivative of carboxylic acid. So, acid chloride reacts with benzene in the presence of anhydrous aluminium chloride. What are we going to get? An acyl group will be substituted in place of the hydrogen. Okay, that means we know in each of these carbon atoms you have hydrogen. So, what happens here? You have an hydrogen here. This hydrogen atom is being substituted by the acyl group here, which is COR. It will be substituted. So what happens? You will get the COR group here, the acyl group here, as well as the H which is being substituted, which is removed, that combines with the chlorine which is present in the acid chloride and forms HCl. So this is the reaction. Okay. So what is getting substituted? The acyl part of the acid chloride. Okay. So for example, benzene reacts with acetyl chloride in presence of anhydrous aluminium chloride to form acetophenone. So what is the product you are getting here? It is a ketone, right? As you can see here, one alkyl group here, another benzyl group is here, and what is the CO? This is C double bond O, right? So on either side you are having 2 alkyl groups or one benzyl group, and on the other side you have another alkyl group. So this is an example of a ketone. Okay, so coming back to this example, we have taken CH3COCl. Okay, and in presence of anhydrous aluminium chloride, what is it going to be substituted? If I am representing the hydrogen here. This hydrogen is being substituted by the acyl group COCH3. So what happens instead of hydrogen there? You will get the COCH3, and the hydrogen which is being replaced combines with the chlorine and forms HCl. So what is the product you are getting? It's a ketone which is acetophenone. So I hope this is clear. Right. Now let's understand the mechanism of Friedel-Crafts acylation. Okay. So the mechanism involves, the first step is formation of an electrophile. So still we are in the electrophilic substitution reactions, right? So what are electrophiles? Yes, which has attraction towards negatively charged substances. That means they must be themselves positively charged or neutral. So which is the electrophile here? CH3CO plus is the electrophile. So first it's the formation of electrolyte. How is this electrolyte formed? Let's see. So what is that we are initially taking here, it is an acid chloride, and we have what else? Anhydrous aluminum chloride also with us. So these two reacts, and what is that you are going to get? You are going to get the carbocation, which is CH3CO plus, as well as AlCl4 minus. The Cl gets attached here. So what happens? It is Cl minus, and this part will be plus and this part will be minus, right? So what happens? You got the carbocation as well as the AlCl4 minus. That is the electrophile. You got the electrophile. Fine. Now what happens? That is the first step. Now the second step is, it's already what we have already studied in the mechanism of all the reactions we have studied in last session. The electrophile attacks benzene to form carbocation. Now what it forms? The electrophile will attack the benzene and form a carbocation. So the first step was formation of electrophile, which is formed. Now this electrophile will attack the benzene, and what it will form? It will form a carbocation. So as you can see here, it will attack in this double bond position, and what will happen? An hydrogen atom is already there, and this CH3CO plus, what will happen? It will get attached here, and the positive charge will be here on the other carbon atom. So you obtained your carbocation. So now you yourself can tell me what will happen next. Yes, this carbocation will stabilize using resonance, right? So as you can see, the carbocation formed is stabilized by resonance, and it is the resonance hybrid of the following structures. Okay, so as you can see here, this is the first structure. What happens is, double bond when it shifts here, as you can see, the double bond shifts here, the positive charge will be here. Now this double bond shifts here, what happens? The double bond will be here, and here the positive charge will be here, right? And this way, in these three positions, it can be there. That means in the ortho position or the para position. So resonance will take place and the carbocations will be stabilized, and this is how we can represent the resonance hybrid of it. It can be in either of this position, that is why it is shown like this. Okay, now the carbocation is stabilized. What is the next step then? Let's see. The carbocation loses a proton to AlCl4 minus to form products, and catalyst AlCl3 is regenerated. Okay, anhydrous aluminum chloride is our catalyst. So that will be regenerated. How? Because of the release or the losing of a proton. So as you can see here, this is your carbocation which you have. Now from the carbocation, this H plus will be removed. And what happens is, H plus will combine with one of the Cl minus and form HCl. Now HCl is formed. What is left there? AlCl3. Right, this Cl minus and HCl will combine and form HCl. You will have AlCl3 which is regenerated, and what is left behind here? Only the acetophenone, COCH3 will be left here. So you got your product. Okay, so I hope this is clear. This is the mechanism. So it's same as that what we have studied for Friedel-Crafts alkylation also. Now the next reaction is combustion. So you already know what is combustion. Yes, combustion is the burning of substances, excess of oxygen, and the products will be carbon dioxide and water, right? So when benzene, we are talking about aromatic hydrocarbons, right? So when benzene is heated in air, it burns with a sooty flame producing carbon dioxide and water. So in excess of oxygen, we are going to burn benzene, we are getting carbon dioxide and water. So this is the equation for the combustion of benzene. This is a balanced chemical equation which is written here. C6H6 is benzene plus 15 by 2 O2. It burns in presence of excess of oxygen to form 6 carbon dioxide and 3 moles of water. So I hope that is clear. So this is combustion. Next one is addition of hydrogen. So you have already studied in organic chemistry also. If you are going to add hydrogen, what will happen to the double bonds or triple bonds? We have already studied this. When we are adding hydrogen, yes, the double bonds will break and become single bonds, right? So the same thing is going to happen here also. Let's see. In the presence of finely divided catalysts like nickel, under pressure, benzene undergoes hydrogenation to give cyclohexane. Hydrogenation means addition of hydrogen. So you have benzene here, to which we are going to add 3 moles of hydrogen in presence of finely divided catalyst like nickel. What happens? You have 3 double bonds here. All of this double bonds will break and form single bonds. That means what you are getting from benzene, you will obtain cyclohexane. All the double bonds will be removed. This process is called as hydrogenation. We are adding hydrogen. Okay. So this is the next reaction, that is addition of hydrogen. Now moving on to the next one, addition of halogen. That means we can also call it as halogenation reaction, right? So benzene undergoes addition reaction with chlorine in the presence of sunlight and gives benzene hexachloride. So we are going to add 3 moles of chlorine in presence of sunlight. So what happens in each of the positions, each of the carbon atoms, 6 carbon atoms, one chlorine atom will be added. So as you can see here, this is an addition reaction. In each of the positions, you can see 6 chlorine atoms. Okay. So now the product obtained is called as benzene hexachloride, BHC. So I hope that is clear. In each of the carbon atom, one chlorine atom will be substituted. One chlorine atom will be added. So as you can see, we have 3 moles means you will totally have 6 atoms of chlorine, right? Moving on to the next one, directive influence of a functional group in mono-substituted benzene. So if you are having a benzene which is mono-substituted, that means it is just having some group which is substituted to it. For example, let's take the example of phenol. That means on benzene ring you have an hydroxy group, OH. Okay, this is mono-substituted. Why? Because it is having only one substitution, one OH group here. Benzene is substituted by an OH group. So this is mono-substituted benzene. Now, if we have to substitute one more group to this, it is based on what group is present here. It is based on that we can predict to which position the next group will be substituted. Whether it will be in the ortho position, para position or meta position, it will decide. Who will decide this? The group which is already present here. So let's see, when the mono-substituted product is to be converted into di-substituted one. That means already one group is there. We have to substitute one more group to it. Okay, the existing substituent, whichever is already present on the benzene ring, directs the incoming group, whichever group is going to be substituted, a particular position. So he will get to decide, the group which is present here will get to decide to which position the incoming group will go, whether it is ortho, para or meta position. This is referred to as directive influence of the group, because it was going to direct the incoming group to ortho, para or meta position. So whichever group is substituted already on the benzene gets to decide the next incoming group where it will go. Okay. So depending upon their directive influence, various groups or substituent functional groups can be divided into 2 categories. So the first one is ortho-para directing, and you have second type which is meta-directing. Okay. So first one is the substituents or groups which direct the incoming groups to ortho and para positions are called as ortho-para directing groups. That's the first type, that is ortho-para directing groups. So there are certain groups which, when there is any other incoming group which is coming, it will direct it into ortho and para position. For examples, methyl group, ethyl group, chlorine, right? Hydroxy group, bromine, all these are examples of ortho-para directing group. If we carry out nitration of phenol, the mixture of ortho and para nitrophenols are formed, and this can be explained by the following resonating structures. So as you can see here, let's take the example of phenol. Okay, on phenol, what is it? It is the OH group, right? So oxygen will have lone pairs of electrons. Now it will undergo resonance. So what will happen? This lone pair of electrons will come here. You will get a double bond here, which you can see here. What happens to the lone pair which has shifted here? It will come in the first ortho position. Now what happens in the next step? This negative charge will become the double bond here. And what happens to this double bond? The double bond will become the negative charge here, lone pair. So you can see now it is in the para position. Now what happens? The negative charge will shift here and become the double bond in the next resonating structure. And what happens? In the next position, the negative charge again will shift here and you will obtain the first structure where you started off with. So these are the resonating structures. So what you can observe here, the negative charges where you can see the electron richness in present in the ortho position, yes, para position as well as the ortho position. So it is in the ortho and para position. So that is why, as the richness of electrons is present in the ortho and para position, the incoming groups will be directed there. Right. From the above resonating structure, it is known that the electron density is more in the ortho and para position. Hence, substitution takes place mainly at these positions. So the electron density, as you can see here, it is in ortho here, para here, ortho here. So it is in ortho and para positions. So it will be easily substituted in the ortho and para position. So all these groups are examples of ortho-para directing groups, and they are also called as activating groups. They are activating groups means, why they are called as activating groups? Because they have the tendency to give electrons towards the benzene and make it more electron rich, and it will increase the reactivity of benzene. It is not taking up electrons from the benzene, it is ready to donate electrons to benzene and make it more electron rich. So such groups are called as activating groups because they are making the benzene more reactive, more activated, right? Okay. Now moving on to the second type, that is the meta-directing groups, also called as the deactivating groups. Let's see. The substituents or groups which direct the incoming group to meta positions are called as meta-directing group. Okay. So NO2, CN, CHO, aldehyde, carboxylic acid, ester, all these are examples of meta-directing groups. So nitration of nitrobenzene produces meta-dinitrobenzene, and again we can explain this, why it is happening, the substitution is happening in the meta positions, or why these groups are acting as meta-directing groups. So let's see the resonance here. So for examples, we have taken the nitro group. So nitro group is an electron withdrawing group. It is not ready to donate its electron, unlike the methyl, ethyl, chloro group, halogen groups, all of that we have already studied. They are all electron donating groups. But nitro group is an electron withdrawing group. So what happens from the benzene ring? The electrons are being taken up by the nitrogen. Okay. So now what happens here? This double bond shifts here and you will get a negative charge here. And the double bond shifts here. What happened? This will become a double bond. As a double bond shifted here, you will get a positive charge here, which is shown here. Right. Okay. Now what happens? This double bond will shift here. The double bond will come here. The positive charge will come here. Now in the next step, what happens is double bond shifts here and the positive charge come here. So now what is the difference between the resonating structure you have seen before and now? In the ortho-para directing and meta-directing. In meta-directing, you can see in the ortho and para position, you are getting a positive charge, right? In the ortho position here, para position here, ortho position here, it is not electron rich now. It is having less density of electrons here, right? So now, will it help in substituting the incoming group more easily? No, right? Because it is having positive charge. It is less electron rich now. Okay, that is why they are also called as the deactivating groups, because it is taking up electrons from the benzene ring. The nitro group is taking up the electrons from the benzene ring. So as you can see in this case, the overall electron density on benzene ring decreases, making further substitution difficult. So in the ortho and para position, as you can see in this ortho position, this para position, and in this ortho position, it will become difficult to substitute another group because the electron richness or the density is overall less there. Right, okay, hence these groups are called deactivating groups, and the electron density on meta position will be comparatively greater. Okay, as there are positive charges in the ortho and para position, the electron density will be less there, but comparatively, who will have the more electron density? That will be the meta positions. So it will get substituted there. Yes. And therefore, electrophile attacks meta position to form meta substitution product. Okay. So I hope the directive influence is clear for you and the examples is also clear for you. Right. Now moving on to the last topic, that is carcinogenicity and toxicity. So benzene and many of its polynuclear compounds are toxic and carcinogenic. That means carcinogenic, we have already discussed this. They causes cancer, right? The polynuclear hydrocarbons are formed due to incomplete combustion of organic materials, right? Organic substances, when it undergoes incomplete combustion, it forms this carcinogenic substances, right? For example, like tobacco, coal and petroleum. They enter into the human body and undergoes various biochemical reactions and finally damage the DNA and causes cancer. So why this is happening? Why these substances are behaving as carcinogenic substances? It is because it is undergoing incomplete combustion and it enters into our body and it damages the DNA and causes cancer. Okay. So all these examples that you can see here, these are examples of carcinogenic substances. They are polynuclear compounds. Okay, that is containing more than one benzene ring. So all these you can see are examples. See, all of these are containing more than one benzene ring, and when it undergoes incomplete combustion, it causes cancer. They are carcinogenic or they are highly toxic to humans. Okay, so by this we come to an end to this chapter, hydrocarbons. So I hope the concepts that we have covered in this whole chapter is clear for you. So in the next session, we'll meet with a new chapter. So that's all for today. Thank you.